Okay, today's lesson is on polarization, and this will wrap up our chapter. And polarizing, there's no formulas or anything to calculate. We just basically, it's mostly theory and to understand kind of a weird thing that we've all witnessed, but it's pretty hard to explain in cases. So over the years, polarization has been around. Anytime you get glare off reflecting on water or off snow and we get this blinding shine, or reflection of sunlight off glass or anything like that, we get this glare. So the reason is, why do we get a glare? And the idea is it's polarization that causes the glare. So what polarizing is, we got to think of, first of all, we got to think of the wave as being sort of a three-dimensional, it expands in every direction. So if we were to look at the end of a wave traveling towards us, it would look kind of like this picture. We'd have this equal wave going in every direction, vibrating in 360 degrees. So what happens then is, once that wave hits a surface like water, part of it gets crunched. So you can see in this picture, just to keep it simple, we got the wave as just being like a XY axis. So you can see once that wave would travel down and hit the water, the vertical part would actually get crunched. So think of it like a basketball. When a basketball bounces and it hits the floor, it kind of compresses, so the vertical part gets crunched and the horizontal stretches out a little bit. So you can see what's going to happen then is that wave gets crunched vertically, stretches out, and that's what gets reflected off. So the idea with polarizing is there's nothing weird going on. The problem is our eyes and brains, we can't figure out what light waves like that look like. So anytime a light wave that's not proportional, so we normally should always have a wave that's sort of equal in height and width, if it gets distorted in any way, our brain doesn't know what to do with it, and we just sort of see it as glare. So to get rid of the glare, we have to try to get that wave back to normal. So if you think of the water wave as being kind of like that after it hits the water, the idea is we just need to make it both the same size. So if we can get the width to match the height, the wave will then be back to being proportional and we'd be able to see it. We'd lose some of the brightness and some of the features of it, but we'd still be able to see it. So what happens is we need to balance it out. So you got to think of like polarizing lenses sort of like being a picket fence. So if you have a fence and we had a skipping rope go through the fence, we could create the wave vertically up and down through the fence boards, but if we tried to go sideways, they would get stopped. The boards would stop the rope and our wave wouldn't go through very good. So what a polarizing filter does then is it just sort of makes those waves back to normal. So you can see in this picture again, we got our normal sun wave hitting the water, it gets crunched down. So once it goes through a polarizing filter, if we have a vertical filter in this case, the vertical part of the wave would go through it just like a rope would go through a fence board, but the horizontal part would get chopped off depending on the width of the cracks. So in this case, what's going to happen then is our wave would come out the same height, but our width would get shortened down, narrower. And if they're the same size, vertically and horizontally, then we'd actually be able to see the picture. So polarizing lenses, that's all they do, is to try to make the wave the same. So quite often, sunglasses, polarizing sunglasses, the idea is just to do exactly this. They usually have vertical lines cut in it, and it's to help cut out the glare off of anything that's shining. So because of that, knowing how to use polarizing lenses can actually work pretty good for photographers. So you can see in this picture, there's a woman talking on the phone, and we're taking a picture through the window. So you can see in this first picture, you get glare off the window, and you can't really see much. If we put a filter on it, we would see that. So the filter on the camera then is just a bunch of vertical lines to chop off the glare that's coming through. And it doesn't necessarily mean it have to be vertical, it could be horizontal, whatever. Depending on whichever way the reflection's going, you might have to turn the lens one way or the other to be able to cut out the glare. So if we think of a polarizing filter as just being sort of a screen with vertical or horizontal cuts, what we would see then is if we rotated them 90 degrees to each other, so if we tried to pass light through a vertical one only, so you can see in this picture here, we got this skipping rope going through the vertical, the waves pass through fine. But then if we try to pass it through a horizontal, they don't. So if we did one vertical first, and then we do a horizontal, that would basically eliminate almost all of the wave, so nothing would pass through. So if you take polarizing lenses, and the easiest sort of example that you guys would know of for polarizing lenses would be 3D movie glasses. So inside the 3D movie glasses, you can see here, they have one lens vertical and one lens horizontal, and you can see the light gets blocked out. So the reason for that is, let's suppose this lens is horizontal, and let's suppose this lens is vertical. And then the second pair of glasses is rotated so that this one would be horizontal, and the other lens then would probably be vertical, like that. So what happens is when we rotate them at 90 degrees, we're basically blocking out all of the vertical and or all the horizontal light at the same time, so we pretty much cancel everything. So how 3D glasses work and how 3D movies work is they basically film a movie twice. So when they're recording the movies and the actors, what they do is they have one camera, and oops, what did I do here? I lost my picture, but that's okay, we don't need it anymore anyway. So what they would do then with your movie is they film one camera, films the movie, and it has a vertical lens on the camera. The other camera films the movie with a horizontal lens. And what they do, anything that they want to have looking 3D, what they do is they film that scene twice, and they just get the actor or whatever they want to be 3D in a different location. So let's suppose, they have a person here, so both cameras film that person at the same time, but then they do a second take and they move, let's suppose they move the person's fist further outwards, and they only film it with this camera, and the other camera just keeps the original image. So what happens is the person's fist will be kind of overlapped. So that's why if you look at a 3D movie without 3D glass on, it looks kind of blurry, because anything that they want to show in 3D is filmed a little bit differently than the original. So then the two images sort of kind of overlap each other and it's not quite aligned, so you get this little bit of a blurry effect. So what happens now is when you're watching the movie with 3D glasses on, one of the lenses is filmed horizontally, or one of the lenses has horizontal polarization, the other one has vertical. So each eye sees what each of the cameras recorded. So if they have a 3D effect where one lens is showing it a little bit different, that you'll see that in one eye, but then you'd see the original image in the second eye, and it's just a brain trick after that. Your brain doesn't know what to do with two different images that aren't quite exactly the same. So what your brain thinks is, well, it's moving forward or it's a little bit further out. So it thinks it's more of a 3D image like what we'd see in real life compared to just a 2D flat movie type of image. And that's all.